In this section, we are going to learn the chain rule. And the chain rule allows us to use the derivatives that we've practiced before, for instance, the power rule derivative, the exponential derivative of logarithms, to look at derivatives of things that are a little more complicated. So as an example, if we're given an exponential growth problem, similar to what we saw earlier, that a of t equals 1000 e to the 0.149 t, we might be asked, what is a prime of 1? We might be asked that directly or indirectly in what is the rate of change after 1 year, if t is in years. And if it was just plain e to the t, we could use what we learned in section 3.2 to find the derivative. But this is a little more complicated. So what we have to use is what is called the chain rule. So the chain rule is for composition of functions. So in this case over here, we have a composition of functions in that if we were to calculate it without the 1000, if we ignore the 1000 right now, just this is a composition of functions. First we have to multiply by 0.149, and then we take that answer and put that into the exponential. And we're going to see some other more complicated composition of functions as our examples for the chain rule too. So when we have composition of functions and we can't do any other simplification, we have the derivative of f composed with g. That's what we're asked to find. Right, and this is notation for f of g of t. So one way of writing this is if we're looking at this as y equals, and we're trying to find this derivative, what we can do is we can let the inside stuff be called something else. So we're going to let z equal g of t. And one way of writing the chain rule is that y prime will be df dz times dz dt. And this is almost like a change of units type of a problem where we multiply so that the dz's cancel. And you're left with the derivative of f with respect to t. With this more complicated z in between. Now, a lot of people don't like the Leibniz rule, chain rule. So another way of looking at the same thing is we have f prime of g of t times g prime of t. And how I verbalize this is I verbalize this as derivative of the outside times derivative of the inside. That's how I verbalize it inside my head as I'm doing the chain rule. This isn't quite everything. It's more complicated than that. Derivative of the outside evaluated at g of t and things like that. But that's how I verbalize it, how I think of the chain rule. Derivative of the outside times the derivative of the inside. So what we're going to have to do is figure out what is the outside and what is the inside. So if we go to this problem, I'll block this off. We are going to think of z as 0.149 times t. And so then if I rewrite this, I'm going to write this as y equals 1000 e to the z. And that is something that we can take the derivative of using section 3.2. dy dz is just 1,000 e to the z. And then we have dz dt the derivative of z with respect to t is 0.149. So what this gives us is that the derivative of our function is 1,000 e to the z. Well, z doesn't make any sense in this case, so I'm going to write what z equals times 0.149. This right here is the derivative of the outside. The derivative of the exponential is just itself again. And this is the derivative of the inside. And so we can simplify this to be, when we multiply 1,000 by 0.49, we get 149 e to the 0.149 t. So if we were asked what a prime of 1 was, it's 149 e to the 0.149, which if we go to a calculator, it is about 172.94. So if this were a growth problem for an investment and t was in years, our rate of change at 1 year would be about $172.94 per year.